Spatial analysis is one of the primary uses for a GIS. Any analytical operation we perform on our spatial or associated attribute data can be considered spatial analysis. Spatial operations are applied to our input data and generate output data. Input can be one-to-many layers, as well as the non-spatial data. Output may also number from one to many layers. Operations also have a spatial scope, the area of the input data that contributes to the output values. Scopes are commonly local, neighborhood, or global. Spatial analysis is the application of operations to coordinate and related attribute data. A chain of spatial operations is often specified with the output of each operation serving as input to the next. There are three aspects of spatial analysis: selecting input data, selecting operations, and specifying an order of applying operations to inputs and intermediate values. Spatial data analysis usually involves using data for one or more layers to create an output. The analysis may be a single operation applied to one data layer, or many operations that integrate data from many layers. Some operations, such as terrain analysis, may take data from one layer and create multiple outputs. For example, we would have elevation as an input, and we would have slope and aspect as two different outputs. The output can be spatial, for example, a new data layer, or a non-spatial relation, a table of some size. Spatial operations have a scope, which is the extent of the area of the input data that is used in the operations. Spatial operations can be characterized as local, neighborhood, and global. A local operation is a spatial operation where the output location, area, or extent comes from operations on that same extent. And that's like we see in the top set of figures. A neighborhood operation is a spatial operation where the output location, area, or extent comes from operations on an area larger than and usually adjacent to the input extent. And we see an example of that in the middle set of figures. A global operation is a spatial operation where the output location, area, or extent comes from operations on the entire input area or extent. And of course, we see this in the bottom set of figures. Spatial data analysis usually involves manipulations or calculation of coordinates or attribute values with various operators or tools, such as selection, reclassification, dissolving, buffering, overlay, and cartographic modeling, which is a combination of the above. We will address all of these in turn, starting with selection. Selection operations identify features that meet one or more conditions. Either attributes or geometry or characteristics of both can be conditions that are used to select or filter input. Once data is selected, it is acted on in some way. The selection can be done with set algebra using operations like greater than, less than, equals, or not equals. Set operations can be composed into more complex selections with Boolean algebra. this is the use of or, and, as well as not. Many spatial operations select sets of features, and adjacency and containment are commonly used selection operations. Here we see adjacency, which is an operation that identifies those features that touch other features. This means they can share a boundary or line. Another form of adjacency is when features share a node or point. And we see an example of this here with the Four Corners area in the southwest. Containment is another spatial selection operation. It identifies all features that contain or surround a set of target features. This figure shows a containment selection on the Mississippi River in the United States. All states that contain some portion of the river or one of its tributaries are selected. As mentioned, spatial analysis usually involves manipulations or calculation of coordinates or attribute variables with various operators or tools such as selection, reclassification, dissolving, buffering, overlay, and cartographic modeling. Next, we discuss reclassification. A reclassification will categorize a set of objects based on a set of conditions. You can consider it as an assignment of features from an existing set of classes to a new set of classes. Classifications are often specified by a table or an array. The table identifies the input class or values as well as the output class for each in this set of input values. This slide shows the use of a table in classifying. It is the classification of a thematic layer. Values are given to specific attributes in the classification table that is used in turn to assign classes to the output layer. An algorithm can be used to automate the classification. The figure in this slide describes a data layer showing a set of neighborhoods with populations that range from 0 to 5,133. An algorithm can divide the input into three classes: high, medium, and low population. We'll show high in black, medium in gray, and low in white in the next several slides. The figure has a bar graph that shows the count of neighborhoods that are found in each bar or bin, a narrow set of population categories. We will apply three different algorithms to this neighborhood to classify it into high, medium, and low, and show the resulting maps and bar graphs. The three algorithms are equal interval, equal area, and natural breaks. We start with equal interval. Equal interval classification is a classification method that assigns an equally spaced set of classes across the range of a variable. And if you'll remember from our statistics class, the range is the high value and you subtract the low value from it. This equal interval classification simply subtracts the lowest value in the classification variable from the highest value and defines equal width boundaries to fit the desired number of classes into the range. The slide illustrates an equal interval classification for the population variable. Three classes assigned over the range of 0 to 5,133 are specified. Each interval is 1/3 of this range. This range is evenly divided by 1711. So we see the various classifications. 0 to 1711 are classed as low. 1712 to 3422 are classed medium. And all counties above 3422 are classed as high. And we see the different color schemes: white, gray, and black. Another common method for class assignment results in an equal area classification. Class boundaries are defined to place an equal proportion of the study area into each of the specified number of classes. This usually leads to a visually balanced map because all classes have approximately equal extents. Equal area classes are often desirable, for example, when working with resources that need to be distributed over equal areas, or when equally sized overlapping sales territories may be specified. An equal area classification is a classification method that assigns classes such that each class corresponds to an equal area. We see this on the left side of the slide. The last algorithm is natural breaks classification, and it looks for obvious breaks. It attempts to identify naturally occurring clusters of data, not clusters based on the spatial relationships, but rather clusters based on an ordering variable. And we see this on the right-hand figure. Once again, spatial analysis usually involves manipulation or calculation of coordinates or attribute variables with various operators or tools such as selection, reclassification, dissolving, buffering, overlays, and cartographic modeling. We now talk about dissolve. Dissolve is a function whose primary purpose is to combine like features within a data layer. Adjacent polygons may have identical values. Dissolve removes or dissolves away the common boundary if they do. Dissolve is used prior to applying area-based selection in spatial analysis to categorize areas as needed before the operation. Dissolves are also helpful in removing unneeded information. After the classification into small, medium, and large size classes, many boundaries become redundant, as we see on the figure on the left before the dissolve. Unneeded boundaries may inflate storage and slow processing. So again, this is what we see in this figure of the counties after we reclass them into low, medium, and high. Next step, just make low, medium, and high blocks with a dissolve. And we see this on the right-hand side. After the dissolve, we no longer have the unnecessary boundaries. We just have the blocks, low, medium, and high. Dissolve operations are usually applied based on a specific dissolve attribute associated with each feature. A value or set of values is identified that belongs in the same grouping. Each line that serves as a boundary between two polygon figures is assessed. The values for the dissolve attribute are compared across the boundary line. If the values are the same, the boundary line is removed or dissolved away. If the values for the dissolve attribute differ across the boundary line is left intact. to reinforce the point, spatial analysis usually involves manipulations or calculation of coordinates or attribute value variables with various operators or tools such as selection, reclassification, dissolving, buffering, overlay, and cartographic modeling. In this slide, we talk about buffering. A buffer is an area that is a polygon or collection of cells that are within specified proximities of a set of features. A buffer operation is one that creates buffer areas. Buffers are used often because spatial analyses are concerned with distance constraints. Many important questions hinge on proximity, the distance between features of interest. Proximity functions modify existing features or create new features that depend in some way on distance. For example, one simple proximity function creates a raster of the minimum distance from a set of features. And this is what we see in the slide. The figure shows a distance function applied to water holes in a wildlife reserve. Water is a crucial resource for nearly all animals, and the reserve managers may wish to ensure that most of the area is within a short distance of water. In this instance, point features are entered that represent the location of permanent water. A proximity function then calculates the distance to all water points for each raster cell. The minimum distance is selected and placed in an output raster data layer, as we see in the slide. The distance function creates a mosaic of what appear to be overlapping circles. Buffering is one of the most commonly used proximity functions. A buffer is a region that is less than or equal to a specified distance from one of the features. Buffers may be determined for point, line, or area features and for both raster or vector data. Buffering is the process of creating buffers. Buffers usually identify areas that are outside some given threshold distance compared to those that are inside some threshold distance. Raster buffers combine a minimum distance function and a binary classification function. A minimum distance function calculates the shortest distance from a set of target features and stores this distance in a raster data layer. The binary classification function splits the raster cells into two classes: those with a distance greater than the threshold value and those with a distance less than or equal to the threshold value. Vector buffering may be applied to point, line, or area features, but regardless of input, buffering always produces an output area with area features. As we see in the slide, all of the output buffers are areas. Simple buffering, also known as fixed distance buffering, is the most common form of vector buffering. Simple buffering identifies areas that are a fixed distance from a set of input features. Simple buffering does not distinguish between regions that are close to one another from those that are close to more than one feature. Buffered circles may overlap, and in simple buffering, the circle boundaries that occur in overlap areas are removed or dissolved. We may have a data layer present as points, as we see in figure A in this slide. A circle with a 10-kilometer radius is drawn around each point. When two or more circles overlap, internal boundaries are dissolved, resulting in some non-circular polygons, as we see in Figure B. Some circular, but two that are non-circular. A buffering variant, referred here as compound buffering, provides more information. Compound buffers maintain all overlapping boundaries, as we see in Figure C. All circles defined by the fixed radius buffer distance are generated. Nested or multi-ring buffering is another common buffering variant, and we see that in Figure D. We may require buffers at multiple distances. In a hazardous waste site example, we can suppose that threshold levels have been established with various actions required for each threshold distance. Variable distance buffers, as we see in this slide, are another common variant of vector buffering. As indicated by the name, the buffer distance is variable and may change among features. The buffer distance may increase in steps. For example, we may have one buffer distance for a given set of features and a different buffer distance for the remaining features. In contrast, the buffer distance may vary smoothly. For example, the buffer distance around a city may be a function of the population density of the city. This figure illustrates the creation of buffers around a river network. These buffers may be used to analyze or restrict land use near rivers. We may wish to increase the buffer distance for larger rivers. The increase in distance may be motivated by an increased likelihood of flooding downstream. So again, to reinforce the point, spatial analysis usually involves manipulations or calculation of coordinates or attribute variables with various operators or tools, such as collection, reclassification, dissolving, buffering, overlay, and cartographic modeling. In this slide, we go over overlays. An overlay is the vertical combination of two or more spatial data layers. Overlay operations are powerful spatial analysis tools and were an important driving force behind the development of GIS technologies. Overlays involve combining spatial and attribute data from two or more spatial data layers, and they are among the most common and powerful spatial data operations. So an overlay is a combination of different data layers. Both spatial and attribute data are combined and a new data layer is created. It requires that the data layers use a common coordinate system. As an example of an overlay application, we may wish to know where there are inexpensive houses in good school districts, or as another example, where whale feeding grounds overlap with proposed oil drilling areas. An overlay may be viewed as the vertical stacking or merger of spatial data. Features in each data layer are set one on top of another, and the points, lines, and area feature boundaries are merged into a single data layer. The attribute data are also combined so that the new data layer includes the information contained in each input data layer. A raster overlay is typically applied to nominal or ordinal data. And again, we discussed those types of data measurement scales in our lecture on mathematics and statistics last class. It is a cell-by-cell process which results in the combination of the two input layers. A raster overlay requires that the input raster systems be compatible. This typically means that they should have the same cell dimension and coordinate system, including the same origin for x and y coordinates. If the cell sizes differ, there will likely be cells in one layer that match different parts of several cells in the second input layer, as we might see in this slide. This may result in ambiguity when defining the input attribute values. Here we see the combination of data in two layers to create the overlay layer data. And here we see a vector overlay and the combining of data from several layers. Topology might be different. Vector overlays often identify line intersection points automatically. Intersecting lines are split and a node is placed at the intersection point. Topology must be recreated for later processing. Any type of vector may be overlain with any other type. Output typically takes the lowest dimension of the inputs. For example, point on polygon would result in a point output layer. So you have a point input layer, a polygon input layer. You're going to end up with a point output layer. This slide illustrates an instance when multiple points in one layer fall within a single polygon in an overlay layer. So we've got two inputs, a polygon layer and a point layer, and three of the points fall within that input polygon. Each point feature has a value for an attribute named class, as we see here. It is not clear which value should be recorded in the output polygon, the class value from A, B, or C. And we see this in the ambiguous result in the top of the right-hand side of the slide. When a point layer is output, and on the slide this is on the bottom right, there is no ambiguity. Each output point feature contains the original point attribute information plus the input polygon feature attributes. This slide illustrates the most common types of vector overlay. Each row in the figure represents an overlay operation with point, line, or polygon input along with the associated output layer. The input data layers are arranged in the left and middle columns, and the output data layer is in the right-hand column. Note that some points in the input do not fall within any polygon or along any line. This results in an unknown or null value assigned for the polygon or line attributes in the output point feature. And they're indicated in the drawing with a negative sign. So, for example, in the top right we see Z minus. So this denotes that the polygon attributes are not recorded. The common ways we apply a vector overlay are in a clip operation, an intersection, or a union. A clip is a cookie cutter approach. The bounding polygon defines a clipped second layer. So that area we see in the bounding layer is applied to the data layer, and we only take values in the data layer that are within those polygons in the bounding layer. All the other are ignored, as we see in the figure on the left here. Neither the bounding polygon attributes nor its spatial data are included in the output layer. Intersection combines data from both layers, but only for the bounding area. The bounding polygon also defines the output layer data from when both layers are combined. Data outside the bounding layer is discarded. And here we see an example of that. We have the intersect between the two polygons, and the polygons themselves are included in the output, unlike the clip operation, as well as the data they bound in the second layer. Union includes all data from both the bounding and data layers. New polygons are formed by the combination of the coordinate data from each layer. Here we have a common feature in both layers. The problem is that each definition is subtly different time, source, materials, so the polygons don't line up exactly right. We then have what are known as slivers. They can only be seen usually on a very large display scale. They take very little space, but they do affect analytical results. So there are methods to reduce or remove slivers. We can redefine the common areas with the highest coordinate accuracy and replace them in all layers before we do the overlay. We can also manually identify and remove them, and we can use a snap distance during the overlay. Networks are a set of connected features, often termed, the features are often termed centers. Centers are connected to at least one and possibly many network links. Links form a network that may have many attributes that specify the flow. And this could be something like a transit cost. Types of problems we might use with network analysis include route selection, resource allocation, territory allocation, and traffic modeling. Links are conduits for movement. Intersections are where links conjoin together. Stops are sources or sinks where resources can enter or exit the network. Centers are node locations which may receive or provide resources. Attributes can be the total amount of resource supplied to or taken from a center. For example, the total water capacity for a reservoir. Barriers are nodes which prevent flow through links, or they're links that have an infinite impedance. Network analysis, also known as network models, are used to represent and analyze the cost, time, delivery, and accumulation of resources along links and between the connected centers. Resources flow to and from the centers through the networks. The concept of a transit cost is key to many network analysis problems. A transit cost reflects the price one pays to move a resource through a segment of the network. Transit costs are typically measured in time, distance, or monetary units. For example, it costs 10 seconds to travel through a link. Route selection involves identifying a best route based on a specified set of criteria. Route selection is often applied to find the least costly route that visits a number of centers. Selection of the best route involves an algorithm that recursively follows a least cost set of arcs, beginning at the current node. A set of interconnected network links is identified, as well as start and destination centers. Resource allocation problems involve the apportionment of a network to centers. One or more allocation centers are defined in a network. Territories are defined for each of these centers. Traffic modeling is another often applied network analysis. Streets are represented by a network of interconnected arcs and nodes. Attributes associated with arcs define travel speed and direction. Attributes associated with nodes identify turns and the time or cost required for each turn. Bottlenecks, transit times, and underused routes may be identified, and this information used to improve traffic management or build additional roads. And this concludes our lecture on spatial analysis.